Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to give an example of application of the theorem of work and energy. So in this example, it's very similar to a video I just made. It's about this biker who's going to roll down this 10-meter tall hill. However, in this example, at the instant shown, right, this biker is going to have a speed of 3 meters per second. And what we're going to do is try to calculate the speed of the biker down here at the bottom. So when applying the theorem of work and energy, we start by labeling the two positions. Here's position 1, here's position 2. And what we notice here, we should take a minute and talk about why would we apply the theorem of work and energy. Well, if we take note that as the biker moves down the hill, they are dropping in potential energy and speeding up, and therefore increasing in kinetic energy. So whenever you see changes in potential and or kinetic energy, the work energy theorem probably is a good way to work a problem. Work energy methods tend to be the simplest way to solve a problem. I always give people this advice: if you can use work energy, do so. It will almost certainly be the simplest way to solve a problem. So we've decided we're going to use work energy because we believe the kinetic energy of the biker is changing. Just like the previous problem, I might start with my kind of motion diagram, the dots to kind of indicate that the bike is speeding up as it goes down this hill. Right. I'm going to write out my work energy theorem. PE1 plus KE1 plus work equals PE2 plus KE2. All right. Potential energies, I'm going to write this up here. Potential energies are equal to mgh terms if we're at the surface of the Earth. I'll always have to decide where do we measure h from. Good news is you get to decide that. I always give this advice: the lowest point in the diagram is usually a good place to do that, so I'm going to call this my datum. And just like I did last time here, I went right through my equations, so I'm going to take a moment and move that. And now I'll put my datum in blue. Okay. Now, I put my datum in such a way that it actually goes through the biker here, and I actually label it in such a way that the 10 meters is, to some point on the biker. The important thing is that the biker is going to drop by 10 meters. Don't get too hung up on the detail about where this line crosses the biker. It's not super important. Plus, this distance is very small compared to the 10 meters anyway. So here's my datum, and again, what is a datum? This is the line of the problem that we're saying the potential energy is 0. PE1 is therefore mgh, where again the h is going to be 10 meters as shown in the picture. KE1, now in my previous video KE1 was 0, but in this problem that I've made up, at this instant this biker's got a reasonable speed here, so we're going to put a 1/2 mv squared for that. Now you'll notice there are two velocities in this problem. There's a velocity in here at state 1 and a velocity at state 2. So it is not good enough to just say v here. I gotta communicate which one. So I'm going to go back and put a 1 on this and put a 1 right here because that's the velocity I'm talking about, the velocity in picture 1. Work term is 0 for the same reasons as my previous video. I'll come back and overview why that one is here in a minute. Okay, position 2 now. The biker's at the datum, so there's no height, therefore no potential energy. And then KE2 is 1/2 mv squared, but again, it's not good enough to just say v. It's v2, the v in picture 2. All right, so again, why is this thing 0? Well, I'm going to take a moment here and put another biker on here and talk about that in a little more detail. So depending on the class you're in, this description may be, maybe something you want to hear, it may not, but I'm going to go ahead and go through it. So if we think about the force vectors acting on this person as they go down the hill, I'm going to go ahead and use my drafting tool here to put those force vectors in. All right, so the first one considers the gravitational force. That force is straight down, and its magnitude is mg. Next, we have surfaces in contact here and here, and that's going to create what we call normal forces. And normal is just a fancy word for perpendicular. Now, even though there's two contact points, we generally would kind of lump those together, call them one force, and that force is basically in this direction. Right? And again, there's my normal. Normal, remember, is just a fancy word for perpendicular. In this case, it's perpendicular to the surface right here. And just like the previous example, we're going to assume frictional forces are small. So basically that's it. These are the only two forces acting on that biker. Now, the big question you have to ask yourself is, are these forces doing work? So let's talk about the mg. Is there work done? Yes or no? And the answer is yes, because the mg is straight down. And when we go from position 1 to position 2, there is a 10-meter displacement in the direction of the normal. However, within the work energy theorem, right, when we look at this PE1 term, mg times h, that term is the work done by gravity as the system moves from 1 to 2. So this is already taken into account. If we try to put another mgh here, we'll be counting it twice. We don't want to do that. Now, the next question, normal. Is there work done? Yes or no? And the answer to that one is no. And the reason is because if I draw the velocity vector, I'm going to do this in red, at the instant shown, the velocity vector is this way at the instant shown, give or take. And the normal always makes a right angle to the velocity, and that's true anywhere along this curve. If you see my video about work and forces that do work and forces that don't, in order for a force to do work, it has to have a component in the direction of motion. So because the normal makes a right angle to the velocity vector, it's not doing any work anywhere in this problem. So all forces are considered. There's no work term to add. So this is the resulting work energy equation, which can be pretty easily solved, I'm hoping. We don't really need the zeros, and notice there's a mass every term. So I get asked about this a lot, about how do we know when the mass divides out? The answer to that question is this, can you divide every term by the mass and have nothing left? 0 over m, 0 over m, this term over m. I've went through and divided every term by the mass. Here they cancel. Here they cancel. 0 over m is 0. 0 over m is 0. And then here they cancel. So v2 squared over 2. If we would have had a work term here, it would have looked like some sort of force times distance, and there'd be nothing to cancel that mass. So in that case, the mass would not have divided out. All right, I'm going to go ahead and put units into this. Now the units are consistent, so I'm going to put NCU for note consistent units. So this is going to be 9.8 times 10 plus, right, V1 is 3, and that's being squared, and divided by 2 equals V2 squared over 2. So I'm going to go ahead and get a value for this. So I get about 102.5 for this term right here. I'm going to rewrite this equation up here. So we're going to have about 102.5 equals v squared over 2. If we multiply by 2, this is now 205 equals v2 squared, and then we would square root both sides. I get about 14.3 out of that. The 205 at this point would have units of meter squared per second squared, and then when we square root it, we'd get meter per second. So V2 is approximately 14.3. I'm just going to round that to 14 meter per second. One thing to take note of, to two significant figures, that may be what I got last time, I can't remember, but when we compare these two terms, this one by far in this example is kind of the dominant term here. So this 3 meter per second did not significantly change that final speed. If we would have probably put a 0 here, it would have been really close. But again, the point of this video was how to take into account multiple velocities in the work energy equation. I hope this video helped demonstrate that. Have a great day.